Hi everyone, this is Dr. K. Kannan, Associate Professor, Department of EC, R.M.K. College of Engineering and Technology. In this lecture video, I am going to talk about the basics of magnetic field and electromagnetic boundary conditions. So the magnetostatics, these are the important points we are going to discuss in the forthcoming lectures. One is the Lorentz force equation, second Ampere's law, vector magnetic potential, Biot-Savart law and its applications, magnetic field intensity and idea of relative permeability, magnetic circuits and the behavior of magnetic materials, boundary conditions, inductance and inductors, magnetic energy, and finally conclude with magnetic forces and torque. So magnetic field intensity, idea of relative permeability, magnetic circuits, behavior of magnetic materials and the boundary conditions. Look at the diagram where the fields going out from inside to the outside and from the outside to the yes. So shows that the field movement. Then so what is magnetic field intensity? Now look at that, the magnetic field. So the region around the magnet is called magnetic field intensity, where the influence of the magnet is going to taking place. So represented by the magnetic field intensity and the magnetic flux density by using magnetic field. Then magnetic lines of force means the magnetic field represented by imaginary lines around the magnet. Then magnetic flux lines means lines of force around the magnetic, and the magnetic field intensity we can represent it by capital H. Here the force experienced by unit north pole of 1 Weber strength and quantitative measure of the strength or weakness of the magnetic field, and it is a ratio of magnetomotive force needed to create a certain flux density B with a particular material per unit length of that material. So this magnetic field intensity measured by Newton per Weber or ampere per meter. This is a unit of magnetic field intensity. Then magnetic flux density represented by capital B. So it represents the total magnetic lines of force. That means magnetic flux crossing a given unit area. So it should be measured in the unit of Tesla or Weber per square meter. Then the basic fundamental postulate of the study magnetic field specify first one divergence and the second one curl of the magnetic flux density in a free space. So del dot B equal to 0 and del cross B equal to mu naught into J. So first one is the divergence and the second one curl of a vector magnetic flux density. So where mu naught is equal to permeability of free space, where the value of mu naught is equal to 4 pi into 10 power minus 7 Henry per meter, where J equal to current density. And del cross B equal to mu naught into J, we can rewrite J in terms of J plus Jm. So 1 by mu naught del cross B equal to J plus Jm, and we can rewrite this one in terms of magnetization. So J plus del cross M, where M equal to magnetization, that is the net dipole moment per unit length. So that J equal to del of capital B divided by mu naught minus M. So we can rewrite the basic postulate related to divergence and curl. Then the new, we can define the fundamental field quantity by using the magnetic field intensity H equal to B by mu naught minus M. Therefore, del cross H is equal to A, that is ampere per meter square. Then the magnetostatics, we are going to maintain del dot B equal to 0 and del cross B equal to always J. So when you are going for the integral, then we are going to get the final equation is called Stokes theorem according to. So integral of H dot dl is equal to I. That is the closed line integral of the magnetic field intensity is equal to the total current enclosed by that given surface. That is called Stokes theorem. Then, so magnetic properties of the medium are linear and isotropic. We can given by M directly proportional to H. Then we are going to remove that direct proportional by a constant is called magnetic susceptibility. So this magnetic susceptibility will not contain any dimension. So that we can write H equal to B by mu naught minus psi M into H. So from that we can find out the total value of B and mu r. Mu r equal to relative permeability. So which is equal to 1 plus psi M. Then this is the comparison of electrostatic and magnetostatic. So in electrostatic we can represent E. Here magnetostatic it is B. That is electric field and magnetic field. Here electric field intensity, electric flux density it is capital D. Here magnetic flux density it is H. Then the permittivity it is epsilon, where it is 1 by mu permeability. So like that we are going to represent from electrostatic and magnetostatic. Then what is magnetic circuit? So the closed path followed by a magnetic lines of forces are magnetic flux line is called a magnetic circuit. So in another way, it is made up of magnetic material having high permeability such as iron, soft steel, etc. So these magnetic circuits are used in various devices like transformer, relays, generator, and galvanometer, etc. So the analysis of the magnetic circuit based on the following equation, already we have seen the basic postulate of the magnetic field: del cross H equal to J and del dot B equal to 0. So this one, it is represented in terms of is a ampere circuit law. So integral H dot dl is equal to I into N. I represent the current flowing through the given N number of coils. So it is equal to gamma M, that is called magnetomotive force. Then the comparison between magnetic circuit and electric circuit. So all we know that the definition and the relationship. In magnetic circuit we are going to talk about a flux, and in electric circuit we are going to talk about current. So here the flux represented in terms of Weber, here current represented in terms of amperes. Then the corresponding mmf equation, that is in magnetic circuit it is a magnetomotive force, in electric circuit it is a electromagnetic force. Then we are going for the the relationship between permanence and condition. It is equal to 1 by reluctance in magnetic circuit, here 1 by resistance. And the analogy, it is permeability, here it is conductivity. Then reluctivity and resistivity, here the density of the magnetic, it is magnetic flux density B, where we are going to find out J. Then magnetic intensity, it is H, here electric intensity, it is E. So like that we are having many different type of difference between electrostatic and magnetostatic. Then the boundary condition. So important next topic, it is a boundary condition for magnetostatic field. So in homogeneous media, electromagnetic quantities vary smoothly and continuously. So at a boundary between dissimilar media, however, it is possible for electromagnetic quantities and to be discontinuous. Okay, so here when you talk about the boundary condition, we have to study the magnetic field intensity and the magnetic flux density at the boundary H and B. So both are the vectors are resolved by using two components. One is a tangential to the boundary, that is parallel to the boundary, and another one normal to the boundary, it is perpendicular to the boundary. So these two components are resolved or derived using Ampere circuit law and Gauss law. Okay, so consider two isotropic and homogeneous linear material at the boundary with a different permeability mu1 and mu2. So consider rectangular path and Gaussian surface to determine the boundary conditions. So here, so look at the diagram. So this is the boundary between two magnetic media, medium 1 and medium 2. Look at the diagram. In medium 1, the permeability is mu1, medium 2, permeability is mu2. So that is one of, that is a rectangular. For example, in the given diagram, A, B, C, D is a rectangular path. So one of it is there in the medium 1 and another of it is in the another medium. And this is for the measurement of magnetic field intensity and magnetic flux density. In terms of, we are considering the Gaussian surfaces. So the above diagram is to measure magnetic field intensity. The below diagram is represented by magnetic flux density, that is H and B. Then we can find out the derivation for electric flux density and magnetic flux density. So here boundary condition for tangential component. So according to Ampere circuit law, we know that integral of H dot dl equal to I. Then we are going to rewrite this equation for all the four paths, because we are considering rectangular path. So that from A to B, B to A, and A to B, B to C, C to D, D to A, and finally the fourth component, so which is equal to I. So the total I enclosed by that surface. Then we are going to have the total equal to the right side, it is K into del W, where K, it is a surface current normal to the path del S. Here rectangular path is a del H and width is a del W. So now look at the diagram. So del H, it is a height, and del width, it is a length, right, from left to right and from top to bottom. So that we are rewriting this K del W in terms of magnetic field intensity H, and what is the height and what is the width. Accordingly, we are going to talk about. So in the diagram, look at that at the boundary, that is exactly at the middle. So the del H is equal to 0, because del H by 2 minus del H by 2, it's going to be a 0, 1. So that the del H is equal to 0. Then in the left side we have K del W, so that the tangential component only is available and the normal component is going to be a 0. So that finally we can write K equal to H tan 1 minus H tan 2. So in vector form we can write it as H bar tan 1 minus H tan 2 bar, which is equal to Kx A1. So this is in the form of vector form. Okay, similarly, we are going for the next one. It is the B. So B, it is a tangential component that can be related with the permeability of the two medium. So B equal to mu H. So B tan 1. Similarly, we can take the tangential component for both medium. So tan 1 and tan 2, and similarly for mu 1 and mu 2. So finally, we can rewrite B tan 1 by mu 1 minus B tan 2 by mu 2 equal to K. So here at the special case, So if the boundary is free of current, then the media is not at all it is a conductor. So that what happen, k equal to 0. So when k equal to 0, what is the value? H tan 1 is equal to H tan 2. Then the tangential component B equal to mu into H. So H equal to B by mu. Then we can rewrite the equation. Finally, we reach B tan 1 by B tan 2 equal to mu 1 by mu 2 equal to mu R1 by mu R2. So this is finally we are going to receive magnetic flux density. Then boundary condition for the normal component. So that one, it is a parallel component. That is here we are going to talk about perpendicular, so that it is a normal component. So here in normal component we are going to talk about the Gauss law. So Gauss law, it is integral of surface integral of b dot ds equal to 0. So like that, this Gauss law is expanded based on the surface. So in the Gaussian surface we have three things. One is top, bottom and lateral. So according to that we are going to rewrite this Gauss law. So top, bottom and lateral. So when you talk about the surface, the level is equal to 0. That means there won't be any height. So the lateral surface we cannot get. We are going to get only top and the bottom. So that what happen, we are equate the top equal to the bottom one. So bn1 del s, and similarly for next one, bottom. So first one, it is a top surface and another one, it is a bottom surface. So finally we are going to conclude the combination of bottom and top surface, so that bn1 del s equal to bn2 del s. So finally we can rewrite bn1 is equal to bn2. Therefore the normal component of magnetic flux density is continuous at the boundary. Like that we have to conclude. So we know that b equal to mu into h, that is relationship between magnetic flux density and magnetic field intensity. So that for medium 1 and 2 we can write mu1 h1 n1 mu2 h2 n2 for medium 1 and 2. So that finally we can conclude h1 n1 divided by h2 n2 is equal to mu2 by mu1 is equal to mu r2 by mu r1. Hence the normal component of magnetic field intensity is not continuous at the boundary. So thank you one and all.